Hey everyone, today the MAE student community is at the Greater Rochester International Airport to examine the primary principles of flight and how they are applied in the real world. In MAE 278, we learn about the principles of lift and drag, wing characteristics, and the fundamentals of fluid dynamics in a practical application.
Using theorems derived by Bernoulli, we can explore key characteristics of an airplane wing and how they contribute to enabling flight.
An aircraft wing's airfoil has a cross-sectional area consisting of a curved upper surface and a flatter lower surface.
As the air moves across the wing, it creates a lower pressure overall above the wing and a higher pressure below the wing. If we integrate these pressures, we can calculate the amount of lift, or the force of lift, acting perpendicular to the wing. We can change the amount of lift generated on a wing by changing the airfoil shape and size.
We use airspeed as a crucial measurement for different phases of flight. To measure airspeed, we use a pitot tube.
This is the pitot tube, which is part of the pitot-static system on the aircraft. It works by taking the dynamic pressure from the wind and compares it to the static pressure on the aircraft to determine what the airspeed is on the airplane.
We credit Lord Riley for creating the drag equation used while flying. This equation relies on the perpendicular area relative to the air velocity squared.
While we try to limit drag in aircraft design, we also use it for our benefit in flap and slat design, such as this. We use it to help control the aircraft at slower speeds, and although it does generate more drag, it generates significantly more lift. We can also use spoilers as extreme drag devices to help slow the aircraft down. For steady and level flight, the thrust created must be equal to the drag in order to not be accelerating or decelerating the aircraft.